So the point is to look at the two integrals in 1.13 and show that individually they go to 0 as n tends to infinity. We shall see that the first piece really doesn't give us any problem. The problem comes from the second piece, as you see in the cot t by 2 appearing in the integral. Before we take up the second piece, the more troublesome part, let us deal with the first piece in equation 1.13, the first integral appearing in equation 1.13. That can be settled quite easily using what we call as the Riemann-Lebesgue lemma. The Riemann-Lebesgue lemma says that if you take a function which is in L1 of AB, if g is in L1 of AB, then we have limit as n tends to infinity from a to b cosine nt gt dt is 0 and the limit as n tends to infinity a to b sine nt gt dt equal to 0. We shall postpone the proof of the Riemann-Lebesgue lemma and we shall continue with the discussion of equation 1.13. Remember, in equation 1.13 we had two integrals and the first of the integral appears here, limit as n tends to infinity minus pi to pi cos nt delta tx dt. Remember what is delta tx? It is f of x minus f of x minus t. The function f is continuous. Therefore, Riemann-Lebesgue lemma applies, and by Riemann-Lebesgue lemma, integral minus pi to pi cosine nt into delta of tx dt goes to 0. So the second piece in equation 1.13 is what we should now focus on. So to complete the proof that the nth partial sum Sn fx converges to f of x as n tends to infinity, all we need is to ensure that limit as n tends to infinity minus pi to pi sine nt cot t by 2 delta t comma x dx is 0. That's equation 1.15. Before we take up this, we shall now replace the cot t by 2 by something simpler. Okay, how does the cotangent function behave? What is cotangent x? Cot x is cos x upon sin x. Cos x behaves like 1 and sin x behaves like x. So how does cot x behave? Cot x behaves like 1 upon x near the origin. So how does cot t by 2 behave? It behaves like 2 upon t near the origin. So let us subtract 2 upon t from cot t by 2 and let us call the difference f of t. So we define f of t equal to cot t by 2 minus 2 by t if t is not equal to 0, and at 0 let us define it to be 0. Why did I do this? Why did I define f of 0 to be 0? Because if I take the limit of f of t as t tends to 0, I am going to get 0. In other words, this f that I had defined in this slide, capital F of t equal to cot t by 2 minus 2 upon t, this is continuous at the origin if I define f of 0 to be 0. So with this prescription, we can apply Riemann-Lebesgue lemma. Integral n tends to infinity minus pi to pi f of t sine nt dt is 0. So go back to equation 1.15. From the cot t by 2, subtract 2 upon t and add 2 upon t. What are you going to get? You are going to get integral minus pi to pi sine nt multiplied with capital F of t. What is it? Cot t by 2 minus 2 by 2. Now this piece again goes to 0 plus the remaining piece. We subtracted 2 by t, so we must add 2 by t. So that will mean I must prove this additional piece goes to 0. So what does that give us? That means our problem of proving Sn fx converging to f of x boils down to checking 1.16 in this slide. Namely, we need to check limit as n tends to infinity minus pi to pi t inverse sine t into f of x minus t minus f of x dt should go to 0. So instead of a cot t by 2, I replaced cot t by 2 by 2 upon t. 2 is an innocent constant, and so we are just reduced to proving 1.16. It is at this juncture that we need to impose additional condition on f of x to ensure the validity of 1.16. In order to establish 1.16, we need some extra hypothesis on the function. Just assuming continuity will not be enough. So what is the extra hypothesis that we must impose on the function? And that is given in definition 4 that appears on the slide. Let's look at what this is. A function f from minus pi to pi is said to be Holder continuous, is said to be of Holder class alpha if mod fx minus fy less than or equal to capital M times mod x minus y to the power alpha, where x and y range over minus pi to pi. The difference mod fx minus fy in absolute value is dominated by m times some fraction of the power of x minus y. Such a function is said to be Holder continuous. That is, the function is said to be of Holder class alpha. Show that if a function f is of Holder class alpha bigger than 1, then f is constant. If the Holder exponent alpha exceeds 1, then the function is constant. If the Holder exponent alpha is 1, such a function is called a Lipschitz function. Such a function is called a Lipschitz function. You are probably familiar with these Lipschitz functions from your differential equations courses. But now we shall only assume that the function is Holder class of Holder exponent alpha bigger than 0 and less than or equal to 1. So now we are ready to state and complete the proof of the basic convergence theorem. So now the theorem is properly formulated. Suppose f from R to R is 2 pi periodic and Holder continuous to order alpha, then the Fourier series of f of x converges pointwise everywhere to f of x. The Fourier series gives you back the function f of x that you started out with. So all we need to show, remember, is that limit as n tends to infinity, integral minus pi to pi, 1 upon t, bracket f of x minus t minus f of x, sine of nt dt is 0. So now let us split the integral into two pieces. Again, I have abbreviated f of x minus t minus f of x with delta. So integral minus pi to pi t inverse capital delta sine nt dt equals the integral over the range mod t less than little delta and over the range mod t between delta and pi, right? The integral from minus pi to pi can be split in this way. Now for the first piece, use the Holder continuity. Let's see how that goes. So now let us write this integral, absolute value of the integral, mod of minus pi to pi t inverse delta of t comma x sine nt dt equal to the modulus of the two pieces, sum of the two pieces. Now use triangle inequality. Less than or equal to capital M times integral dt by t to the power 1 minus alpha. Remember that mod delta, mod capital delta, because of Holder continuity, is less than or equal to m times mod of t to the power alpha. So you see what has happened here, what you need to observe is 1 upon t is not integrable near the origin. thanks to Holder continuity, the capital delta gets bounded by t to the power alpha. So some power of t gets eaten up by the t to the power alpha, and you're getting the integral to be dominated by m times integral dt by mod t to the power 1 minus alpha over the range mod t less than delta. The second piece, I'm keeping it as it is. I'm not touching the second piece. Now, the first piece can be integrated. It's an even function. You're integrating an even function over minus delta delta. So, it will be twice m integral dt by t to the power 1 minus alpha from 0 to delta. Just complete the integration. You get 2m by alpha into small delta to the power alpha. Now remember that small delta is going to be small. So now let us bring in the epsilon. Let epsilon greater than 0 be arbitrary. Select the delta greater than 0 in such a way that 2m by alpha delta to the power alpha is less than epsilon by 2. So the first piece in the middle of the slide gets less than epsilon by 2. And now we have the second piece. Now the second piece, remember, 1 upon t is continuous from delta to pi. The problem is near the origin, but the origin is far away. We are cut out an interval from minus delta to delta. So the place where the 1 upon t is misbehaving has been excised out. So we have got an integral from delta to pi. We have got an integral from delta to pi. 1 upon t is continuous, capital delta is continuous, and we have got a sine nt. So Riemann-Lebesgue lemma. Riemann-Lebesgue lemma says that the second piece goes to 0 as n tends to infinity. So it must be less than epsilon by 2 for all n bigger than n naught, and the proof is completed. Okay, so with this thing, we have finished the proof of the basic convergence theorem. So if a function is 2 pi periodic and Holder continuous on minus pi to pi, then the Fourier series of f converges everywhere to f of x. So now let's move on to the proof of the Riemann-Lebesgue lemma. Remember that we use the Riemann-Lebesgue lemma often in this proof. At many places we use the Riemann-Lebesgue lemma, and so we must look at the proof of the Riemann-Lebesgue lemma. The Riemann-Lebesgue lemma is really very easy to prove. The proof proceeds in 4 easy steps. So what is given to you? Function that is given to you is in L1 of AB. The function that's given to you is in L1 of AB. So let epsilon greater than 0 be arbitrary. The first thing is, let us verify the Riemann-Lebesgue lemma for the case when g of t is t to the power k. What are we supposed to check? Integral from a to b t to the power k sine nt dt goes to 0, and integral t to the power k cos nt dt goes to 0. We can directly integrate and we can check it. Integrate by parts and check it directly. So the case is very easy when g of t is t to the power k. So the Riemann-Lebesgue lemma has been established for g of t equal to t to the power k. Now suppose I prove it for g of t equal to t to the power k, then I can prove it for all polynomials by taking linear combinations. So the Riemann-Lebesgue lemma has been established for polynomials. Now look at the function f. The function f is in L1 of AB. So from L1, we must first move on to a continuous function. That should remind you of Lusin's theorem. What is Lusin's theorem? Every L1 function can be approximated by a continuous function in L1 norm. This is the one of the 3 Littlewood's principles, that a Lebesgue integrable function can be approximated arbitrarily closely by a continuous function. We pick a function h such that h is continuous and integral from a to b mod gt minus ht dt less than epsilon by 3 times b minus a. Now let us recall the Weierstrass approximation theorem. The Weierstrass approximation theorem says that every continuous function can be approximated by a polynomial pt. So pick up a polynomial pt such that integral a to b mod ht minus pt dt less than epsilon by 3 times b minus a. Add these two. What do we get? Integral a to b mod gt minus pt dt less than 2 epsilon by 3 times b minus a. All right. So now we are ready to complete the proof of the Riemann-Lebesgue lemma. So let us look at integral a to b gt sin nt dt. Add and subtract a pt. So we get gt minus pt sin nt plus integral a to b pt sin nt dt. The first piece is less than or equal to integral a to b mod gt minus pt dt plus the second piece is mod of integral a to b pt sin nt. What about the first piece? We know that the first piece is less than 2 by 3 epsilon. And the second piece, we already proved the Riemann-Lebesgue lemma for polynomials, remember? So integral a to b pt sin nt dt goes to 0 as n goes to infinity. So there exists an n naught such that for all n bigger than or equal to n naught, integral of the whole thing is less than epsilon. So the proof is thereby completed. So the proof of the Riemann-Lebesgue lemma proceeds in 4 easy steps. So first let us take a g in L1 of AB. Okay, g is the given function which is in L1 and let epsilon greater than 0 be arbitrary. First thing to do would be to verify the Riemann-Lebesgue lemma in the simple case when g of t equal to t to the power k. So for example, when g of t equal to 1, when g of t equal to t, g of t equal to t squared, etc. Directly check, directly integrate from a to b gt sin nt dt and verify that it goes to 0. Similarly, integral from a to b gt cos nt dt, directly integrate and check that it goes to 0. So for the simple case when g of t equal to t to the power k, the job is done. So now let us take linear combinations and let us observe that the job is equally done when g of t is a polynomial p of t. Is that okay? So for polynomials, we have proved the Riemann-Lebesgue lemma. Now how to proceed further? You have taken this function g, we must first approximate the function g by a continuous function. Remember that every L1 function can be approximated by a continuous function in L1 norm. That is the famous theorem of Lusin. It's called Lusin's theorem. It is one of the Littlewood's 3 principles that you read about in Royden's important book on real analysis, that measurable functions can be approximated by continuous functions. Measurable sets can be approximated by open sets. Pointwise convergence can be approximated by uniform convergence. These are the Littlewood's 3 principles, and this is one of the Littlewood's 3 principles. Our function g is in L1, so I can approximate this function by a continuous function. So we pick up a continuous function h of t such that integral from a to b mod gt minus ht dt less than epsilon by 3. Okay. Now take this continuous function h of t and approximate it by a polynomial. The Weierstrass approximation theorem asserts that every continuous function on a closed interval can be approximated by a sequence of polynomials. So we pick a polynomial pt such that pt minus ht is small in supremum. So supremum of mod ht minus pt is very small. If the supremum is small, then the integral is going to be even smaller. So integral a to b mod ht minus pt is going to be less than or equal to b minus a times the supremum. So if I secure that the supremum of ht minus pt is less than epsilon by 3 times b minus a, then we conclude that integral a to b mod ht minus pt dt less than epsilon by 3, which is the second displayed equation in your slide. Adding these two, we conclude integral a to b mod gt minus pt less than 2/3 epsilon. Now let us proceed further. So finally, integral a to b gt sin nt dt. What do? I add and subtract a pt. It will be less than or equal to mod integral a to b gt minus pt into sin t dt plus mod integral a to b pt sin nt dt. Look at the first piece. Take the absolute value inside the integral. Take the absolute value inside the integral. Mod sin nt is less than 1. So we get what? Integral a to b mod gt minus pt dt. But that piece is less than 2/3 epsilon from the previous slide. Now look at the last piece. Integral a to b pt sin nt dt. But that goes to 0 because we have verified Riemann-Lebesgue lemma for polynomials. So with this epsilon, there must exist an n naught such that for n bigger than or equal to n naught, this integral will be less than epsilon by 3. So mod integral a to b pt sin nt dt is less than epsilon by 3. So the whole thing is going to be less than epsilon for n bigger than or equal to n naught. And the proof of the Riemann-Lebesgue lemma is thereby completed. So now let us look at what is the issue with continuous functions. We have assumed that if the function f is Holder continuous to exponent alpha bigger than 0 and 2 pi periodic, then the Fourier series converges to the original function that you started out with. Can I relax Holder continuity? Can I just work only with continuous functions? I mentioned that just continuity would not suffice. For a long time, people tried to work with only continuous functions. They tried to prove the convergence of Fourier series for continuous functions. Even Dirichlet tried to do this. Paul Dubois-Reymond, after several failed attempts at trying to prove this, finally produced a counterexample in 1875. The result is not true. If you take a continuous function, the Fourier series of the continuous function may not converge. In fact, this problem is going to happen with a majority of the continuous functions. A majority of continuous functions will exhibit this errant behavior. But to explain what I mean by this, you will have to bring in some more concepts from point set topology. You have to use the Baire category theorem from general topology courses. And using the Baire category theorem, you can prove that a majority of the continuous functions, they exhibit this errant behavior, namely their Fourier series will not converge in general. The proof of this result is originally due to Stefan Banach, and it is available in most modern texts. We shall try and come back to this idea, and we'll try to prove this if time permits later in this course. So now we must now move on to looking at a simple example of a function which is Holder continuous. So the classic example that I am taking is f of x equal to mod x when mod x is less than or equal to pi. So what is the function? It's mod x, like this. That's a graph, and you can extend it as a 2 pi periodic function, and you get a triangular wave pattern. So it's a nice Lipschitz function. So I can compute the Fourier coefficients, and the Fourier series will give you back the function f of x because of the basic convergence theorem. We had spent a lot of time and we had taken a lot of trouble in proving the basic convergence theorem, and now we must reap its benefits. The function is an even function, so Bn is straight away going to be 0. I ask you to compute the other Fourier coefficients a0 and an, write down the Fourier series, and the Fourier series will give you back the function pointwise. Namely, the last displayed equation in the slide holds mod x equal to pi by 2 minus summation k from 1 to infinity 4 cosine 2k minus 1 x upon pi times 2k minus 1 the whole squared. This holds for all values of x because the function was Lipschitz. So let us put x equal to 0. Let us put x equal to 0, and what do you get? Left hand side is 0. So do some little bit of rearrangement and you will get a beautiful formula. You will be able to find the sum of the series 1 plus 1 upon 3 squared plus 1 upon 5 squared plus 1 upon 7 squared plus dot dot dot. The answer is pi squared by 8. So that's a very instructive example to work out. So I leave it to you to carry this to completion, and please calculate the Fourier coefficients and obtain this formula that appears on the slide. Okay, so we'll stop here for now and we'll continue later.